dear professors and dear researchers, good morning. I am Mohammad Zubair from Hanyang University, and I'm going to present about process modeling and design of amine-based CO2 absorption process to capture CO2 from PSA tail gas stream of the SMR-based hydrogen production process. Here are the contents of my presentation: introduction, then some literature review, then research methodology, research objectives, methodology, and some research discussion, and finally the conclusion. Global warming is the burning issue of time, and we know well that greenhouse gas emissions are the main cause, and more particularly carbon dioxide is the main cause. So researchers are doing their efforts to develop the processes to capture the carbon dioxide. And in current scenario, in all over the world, the carbon dioxide emissions, statistically, if we see that in the last few decades, the emissions have been significantly increased. And therefore, new policies have been developed and are being implemented to reduce the CO2 emissions so that the global warming issue can be tackled. However, if you look on the current policies implementation, then it's not in that good scenario that it could control the CO2 emissions in a controlled way. So in the Paris Agreement, economists agreed to set the net zero CO2 emissions goal. But in the current scenario, if we look, then the CO2 emissions are increasing so significantly that it is not expected that this goal of net zero CO2 emissions will be achieved if the revolutionary efforts are not made. So in this case, hydrogen is the most attractive fuel because hydrogen can be used as an alternative at any position. Like we can use it in transportation sector, in the industrial sector, everywhere. So that's why hydrogen is probably the most attractive alternative fuel and the clean fuel. And most of the hydrogen is produced from using the established commercial technology, that is the reforming process. And more particularly, steam methane reforming process is the well-established commercial technology to produce hydrogen. However, issue is that besides this hydrogen production, this process gives us a lot of carbon dioxide emissions. So we have to tackle this problem by integrating good CO2 capturing process. And these days, many researchers are trying to implement or develop the good process of CO2 capture to integrate with the already established SMR-based hydrogen production technology. Here we can see the schematic diagram for the SMR-based hydrogen production process. And we can see that basically the feed gas and the fuel goes into the reformer where it converts into the syngas, and finally it's in the next step the carbon monoxide is further converted into the carbon dioxide, and then it passes to the pressure swing adsorption, that is PSA, to remove the hydrogen. And then here we can see we have the multiple streams available to capture CO2. The first stream we can see that there is location 1 as shown here is with the flue gas. This flue gas contains almost all the CO2 that produced in the process. And the next location we can see that is PSA inlet, that is the feed to the PSA. It contains CO2 which is around like 16%. And there is another stream available, that is the location 3 we can see. It's the PSA tail gas, which contains around 50% of CO2. So there are 3 locations. We can capture CO2 in any of the location, and there are the pros and cons for each of the location. So if you want to capture all the carbon dioxide produced in the process, then we can capture using the flue gas stream. And if we want to partially capture the carbon dioxide, then we can go for either to the PSA inlet and or the PSA tail gas stream. Definitely we would like to capture flue for the most of the carbon dioxide produced, but that is quite expensive. So mostly the carbon dioxide is captured from the PSA inlet stream or the PSA tail gas. There are several technologies available to capture this carbon dioxide, like absorption membrane, or cryogenic separation. However, chemical absorption is considered as the most established and well-recognized technology to capture carbon dioxide because of the multiple reasons. For instance, it can capture CO2, remove CO2 with a high selectivity. But if we compare with the membrane separation technology, generally membrane is very attractive because it's a very easy to implement and it's not that expensive technology, but this membrane technology is facing the issue of selectivity. So regarding the selectivity and capacity, still chemical absorption is the well-attractive technology, although it's expensive. Now here is the brief literature review that many researchers have done the efforts on the analysis and modern development and the economic analysis of CO2 capture process, particularly using the absorption techniques and using the amine solvents for the SMR-based hydrogen production system. So here are the few researchers, shown here, and we can see that most of the researchers target to capture the CO2 in the PSA inlet stream, that is the PSA feed gas stream, using the MDA solvent or MDA with some promoter. Basically, why they did it? The reason is that this stream, the PSA inlet, that is the PSA feed stream, is attractive because of the high partial pressures. So using the high partial pressure, they can capture the CO2 in an economical way. But there is PSA inlet stream. This PSA inlet stream basically contains high CO2 concentrations. So this is also attractive in that case. But this is not much attended by the researchers. For example, I've shown you one study. In this study, MDA solvent has been implemented to capture CO2 from the PSA in tail gas stream. And in this study, basically the different process configurations have been tested for the optimal solution for the minimum regeneration energy of the solvent. So this is we can say the conclusion of the literature review, that most of the studies focus on the PSA feed stream to capture CO2, and there are not much studies on PSA tail gas. And to manage the economy, in case of the PSA tail gas stream to capture CO2, that is the operating pressure, because this stream is available with the high CO2 concentration but at low pressure. So we have to increase the pressure to absorb the CO2 in the amine solvent. So generally it is operated at higher pressure, and we need a compressor to compress the gas. And the study I mentioned is at the constant pressure conditions. So here it is mandatory or to get the good economy, we have to get the optimal pressure conditions for the PSA inlet stream. So in the methodology, to simulate the absorption process, we have implemented the rate-based model. The our earlier published model is implemented to simulate the absorption process for the PSA inlet stream processing. So here we can see these are the basic equations of the material energy balance, and these are the interfacial mass transfer expressions, which shows here we can see this is the CO2 equilibrium concentration that is determined using the Kant-Heisenberg model, and here the enhancement factor that defines the rate of kinetics of the reaction is estimated using the Valence correlation. And this flow describes the computational procedure of the rate-based model. So we can see that at the beginning, the calculation begin at the top of the column, and here finally this calculation is repeated for 2 to 10 bar operating pressure for the PSA inlet stream, and to determine the optimal pressure conditions. This shows the schematic diagram for the economic analysis. For the economic analysis, it is restricted in our study. We have first initially restricted to the absorber only. And we determined the capital cost and operating cost. And in the capital cost, we use the absorber column and the pump and the compressor. And similarly for the estimation of operating cost, we use the electricity consumption cost for the compressor and the pump. So it shows the schematic here. We can see that how the absorber cost is estimated using the step-by-step, like the calculation of the absorber, the vessel, and then the packing, installation cost, and the other factors. And then similarly the pump cost and the compressor cost are estimated. And finally the electricity costs are estimated for using the unit cost of the electricity, and then the compressional cost calculated using the electricity cost consumption on the compressor. So here are the brief results we can see. It shows the total packing height as a function of operating pressure in the PSA inlet stream. We see as the pressure is raised, the packing height is decreased. Definitely this is because of the increasing of the solubility. So in case of MDA, this is MDA solvent, so it's significantly the solubility is increased with the pressure. So as the pressure is raised, we can see the solubility is increased, or the packing height is decreased, and column diameter is also decreased because of increasing the pressure and as the density is increased. So this profile basically shows the total solvent flow rate requirement and with the CO2 loading. So we can see that basically increasing the pressure is compensated the CO2 solubility. So the loading and solvent concentrations are almost same. So here it shows the absorber purchase cost, and we can see that this is just reflecting the profile with the, it was the CO2, as it was the absorber height, because it is mainly the function of, we can say, of the height. As the height is decreased, so the capital cost of the absorber is decreased. Similarly, this shows the cost of the pump, estimated cost of the pump and the compressor. We can see pressure is increased, so the compressor cost is increased. But the pressure, with the pump we see first it decreased and then started increasing, because it is first decreased because of the height, then since the pressure is increasing, so pressure definitely also impacts the cost of the pump. Here we can see the estimated electricity cost for the pump and compressor. So it's also reflecting the capital cost of compressor and pump, because generally the factors are same. So here we can see the total capital and operating cost according to the factors we considered. So here we can see the total capital and operation cost. We see that it is decreasing and decreasing, and finally it's the minimum at this 9 atm pressure, and then it started increasing. So this is the optimal pressure we can use for to process the PSA inlet stream to capture carbon dioxide using the MDA solvent. So the PSA tail gas stream can be used to capture CO2 using the optimal pressure conditions And in our future work, we will consider the whole process to analyze the economy of the process. And I would like to acknowledge the research grant to start this research work. And and thank you very much.
Okay, any questions? Okay, Dr. Jubir, nice presentation. It's like you have shown us 3 locations where like, we can capture the CO2, right?
Okay, this is
so. Yeah, depending on the location, like the CO2 concentration is different.
Yeah, exactly.
Depending on that, maybe our choice for the absorption technology is different, right?
Yeah, actually, although we can implement absorption technology at any location, we can implement, but definitely we have to make the condition like the pressure conditions. But we can implement absorption at all the locations, and there are the pros and cons in terms of the CO2 concentration. Yes, we compare, for example, maybe you were asking that how we compare the absorption technology with other technology in terms of the locations. Yes, this matters. This matters, like for this PSA tail gas, there are the studies available implementing the cryogenic. Yes, there are. So we have to compare by accounting for the whole process. So because there is in absorption there is a game of the solvents. As we can improve the solvent, it can increase the economy. So there is no conclusive remarks to say that this technology is the best. So this race is continuing.
Okay, please join me thanks to Dr. Jubir.